Hello, welcome to Simplifying Trigonometric Expressions. If you'll notice on the bottom of the page, I have tons of identities, which can be found on your yellow sheet. And first thing I'm going to do is simplify this expression. These are my answer choices. I'm going to see which one it is. One of the strategies I use is always getting things down to sines and cosines. So tan I would rewrite as sine x over cosine x. Cosecant x I'd rewrite as 1 over sine x. I like that because, wow, when you multiply, these cancel. And I'm left with 1 over cosine x, which is secant x. That's my answer choice. Here's another example. If you look down at the bottom of your page, this should scream to you Pythag identity. If it doesn't now, it eventually will. Here is my Pythag identity. I'm going to rewrite that so that I can isolate 1 minus cosine squared. So I'm going to do sine squared plus cosine squared equals 1. I'll subtract cosine squared from both sides. Sine squared equals 1 minus cosine squared. So this is equivalent to sine squared x. So now I have sine squared x times cosecant x. Well, I'm going to rewrite this using sines and cosines. Sine squared x times 1 over sine x. One of these sines will cancel with one of these, which gives me sine x. In case you've forgotten, sine squared x is the same as sine x times sine x. That's why only one of them cancels and you're left with a sine x, which happens to be an answer choice. So we're going to now simplify cosine beta, tan beta. Beta is just another variable, x, theta, beta, alpha. I just don't want you to get scared when you see different letters. Same identities on your bottom, but I'm going to rewrite it. First thing I'm going to do is rewrite tangent as sine over cosine. You notice how nice it is when you rewrite it? Cancel, and I get sine of beta. Let's try another one. Simplify this. First, I see this first, and I would write 1 over sine squared x. I would screw that up. 1 over cosine squared x. And I get rid of this thing. This says Pythag identity. So I'm going to rewrite this Pythag identity and solve for 1 minus sine squared. What does that equal? Well, cosine squared equals 1 minus sine squared. So this is cosine squared x, and I'll stick it over 1. Oh, that's helpful. Those cancel, and this simplifies to 1. Yet another example. This looks complicated. Whenever I see a division problem, I first rewrite it so your division goes sideways. Now I'm going to change this to the 1 over sine theta divided by 1 over cosine theta. In order to divide fractions, you multiply by the reciprocal. So I'll flip this fraction and change it to a multiplication problem. Multiply fractions straight across, so I get cosine theta over sine theta, and that just happens to be cotangent theta. Now let's try simplifying this one. Anything scream out at you? Does to me. Right down here. This is 1 divided by tan squared x plus 1. You didn't expect that, did you? Now I'm going to do 1 divided by secant squared x, because this is equivalent to secant squared x. Well, I'm going to write secant squared x as 1 over cosine squared x. Now I need to multiply by the reciprocal, cosine squared x over 1, which gives me cosine squared x. So this simplifies to cosine squared x. So sometimes, though, we can factor to simplify. So first I'm going to factor. So I'm going to pull out my GCF, which happens to be sine squared. And then this looks like a Pythag identity. I'm going to rearrange this Pythag identity, and that gets me cotangent squared u. So this would be sine squared times cotangent squared theta. I'm going to change cotangent squared into cosine squared theta over sine squared theta. Stick this over 1, cancels. This simplifies to cosine squared theta. Here, I'm still going to use factoring as a strategy. You can factor however you want. I'm going to do an empty box thing. This is cosine to the 4th theta. 1 times 1 gives me 1. I'm going to do cosine squared theta here, cosine squared theta here. But I need a negative 2. This would give me a positive 2. If I make them both negative, get 2 negatives. So get 1 minus cosine squared theta squared. This is equivalent to sine squared theta. Squared now means I have 4 of them. Sine to the 4th theta. Remember, this is the same as saying sine theta squared. Squared. It's just when you write trigonometric functions, that's where the exponent is located. So we're going to simplify this. That looks horrible. Let's get a common denominator, because that's what we learned to do with fractions many years ago. So I'll multiply this by secant theta minus 1 over secant theta minus 1. Because if I multiply by 1, it's the same as multiplying, leaving it by itself. And if I multiply this side by secant theta plus 1 over secant theta plus 1, it's the same as multiplying it by 1. So now my denominator becomes secant theta minus 1, secant theta plus 1. And my numerator becomes secant theta minus 1 plus secant theta plus 1. When I multiply on my denominators, I get secant squared theta minus 1. You could do an area model if you wanted to see. But these two boxes would cancel out, and I get secant squared here, negative 1 here. My numerator becomes 2 secant theta. The 1's cancel, and I have 2 secants. I could further change this because I have a Pythag identity. Secant squared minus 1 is equivalent to tan squared. So I get 2 secant theta divided by tan squared theta. I'll continue to rewrite that using sines and cosines. Sine squared theta over cosine squared theta. And see if that helps me at all. And I should probably rewrite this one too. So I am going to give myself a little more room over here. So notice I'm going to come right over here and begin again. 2 over cosine theta divided by, so it's multiplied by the reciprocal, cosine squared theta over sine squared theta. This will cancel with one of these, and I get cosine theta over sine squared theta. I don't like to see the sine squared in the denominator, so I'll make my final answer cosine theta cosecant squared theta. So let's rewrite this so it doesn't have a fraction. So I'm going to multiply by tan x minus secant x in the numerator and in the denominator. Why? Because if I multiply by the opposite, I'm going to get a tan squared x minus secant squared x, which looks like a manipulated Pythag identity. 1 plus tan squared equals secant squared. If I subtract 1 from both sides, then I subtract secant from both sides. So this equals negative 1. That's kind of convenient. So then I get tan x minus secant x in my numerator. So I get tan x minus secant x divided by negative 1, which allows me to break into parts and get negative tan x plus secant x. So that is how I would simplify some trigonometric identities. So let's re-evaluate some of the strategies here. First, change things to sines and cosines. That cancels out a lot of items. Second of all, you can look for Pythagorean identities. Those come up all the time. You should write division sideways. Always write the division sideways because that becomes easier to multiply by the reciprocal. Another key item is if you rewrite sideways, look for Pythagorean identities still. I would put items that are binomials in parentheses when I rewrite sideways. Then another one is to factor. Factoring becomes very beneficial for you. And you can factor using all the different factoring methods. The next thing is get a common denominator. That's very important. And multiplying by reciprocals to get common denominators usually make Pythagorean identities, as they did here as well. And don't forget, you can break items into two different fractions. This becomes tan x over -1 minus secant x over -1. And breaking items into two fractions can also become beneficial.